Good morning, good afternoon, good evening to all of you from wherever you might be logged in. Welcome to the Concord Battery Virtual IA Renewal Seminar. Our HET presentation today is titled Boosting Your Knowledge of Turbocharging Systems. My name is Tim Gaunt. I am an AMP IA, and I am part of the Hartzell Engine Tech Product and Technical Support Group. I want to say a big thank you to all of you participating, of course, and especially to Chris Holder and Concord Battery for hosting this educational safety training forum. I think we owe Chris and Concord a big round of gratitude because he has been holding us all together during those COVID years. He's been holding us together with these virtual IA renewals, and we really do appreciate that, and Concord Battery for their support. Got to put this screen up there. That's why it says stop. Says this presentation is intended as reference and safety educational material only and is not to be used as the primary source for maintenance, service, or overhaul of HET products. There are numerous stories that I could tell you, including one that just happened this morning, of people that are using things that come off the internet, things that come off the YouTubes, things that come off of presentations, and they're trying to use it for actual maintenance. And we all know as IAs, you have to have approved data to perform maintenance. And in some cases, these people are not using approved data. So be real careful about what's coming into your shop, because sometimes it's real hard to tell what one of those owners out there may have done. Little history on Hartzell Engine Tech. We were founded in 2010 when the parent company for Hartzell Propeller purchased the assets of Kelly Aerospace Energy Systems. Since 2010, we've added on several different companies between Lamar and Jasco and Plain Power and C&D. We also added T&W Aerospace. And then in 2020, we added Aerospace Welding, AWI and AMI, and Quality Aircraft Accessories, which is located in Tulsa, Oklahoma. And we are all part of the new brand of Hartzell Aviation. We took the company here just at this past Oshkosh. And we went ahead and broke the company into three major divisions, which is Hartzell Propeller, Hartzell Engine Tech, which is us, and Hartzell Aerospace Welding, all under the Hartzell Aviation banner. Some of the product lines that we actually have at HET, we have the Aeroforce turbochargers, Plain Power alternators, SkyTech starters, Janitrol aero heaters, Fuelcraft, fuel pumps, and then of course, Quality Aircraft Accessories is considered a brand under the HET product line. It can get a little confusing because all of the alternators, no matter what we manufacture, are considered Plain Power. So the days of Prestolite and Ford and Chrysler and all that's gone. Same thing with turbochargers. We have anything that was Kelly, Air Research, Garrett, all those are now considered Aeroforce. Doesn't mean much to you because you're just going to go by part numbers. And if you call me, you're going to say, I have a blah, blah, blah part, and we're just going to move on from there. Home base is in Montgomery, Alabama, and that is wintertime for us, for some of you that might be out there actually suffering from wintertime. We do have aftermarket and OE support. It's interesting because we just went through, and the folks that we have here on the technical support side, we have Alan Bufkin and Jackie Gilland, Seth White. On the sales side, we have John Heitland, Rodney Arnold, and Wade Hill. And we went through, and I wanted you all to know that we have technical expertise on our products in that we actually have, 3 AMPs, 2 IAs, 2 pilots, and 2 retired military, which you know how they are. So that can always kind of work out that way. All of our manuals that are published are available electronically through aircraft technical publishers. The turbocharger manuals and the valves and control manuals are available through ATP by subscription on a subscription basis, electronically by a subscription basis. RSF, we have what we call RSFs. This is a recommended service facility for HET, and it's for all the turbocharger related components. What's good about the RSFs is that they are required to carry product liability insurance. They are authorized to perform warranty evaluation and repairs. This is important because we'll get a lot of calls of folks that say, I have a turbocharger that's leaking. Well, for us that have been dealing with turbochargers for years, we know that there's no true oil seal in any of the 400 series turbochargers, which means they are going to leak. So you got to be real careful about saying you have a leaking turbocharger. But if that's the way it is, it can be sent into one of our RSFs, and that RSF can take that turbocharger apart, verify there's no problem with materials or workmanship, put it back together, and charge you a nominal fee for that inspection. If you send it here to the factory, good luck. It's going to be a while before we get to it. If we take it apart and find nothing wrong, warranty is going to be denied and you're going to get the thing back in pieces. Another advantage to an RSF is all the work is performed but factory audited to current manuals. Nobody's using like in-house specifications. Pretty quick turn on turbos, valves, and controls. You can work that out with the shop, and they're pre-approved network of shops. And those shops are, of course, we have Quality Aircraft Accessories. Obviously, we own them, so that's logical. They're in Tulsa, Oklahoma, and Fort Lauderdale, Florida. We have Aero Recip in Manitoba, Canada. We have Aero approved turbo components down in Vero Beach, Florida, and Main Turbo Systems out in Visalia, California. All right, away we go. You know, you got two ways of doing this. You've got supercharging and you have turbocharging. Both allow you to push air into the engine more so than what's available as the standard day. And the whole idea is that how you're going to get it there and what's the best way for an aircraft to do it. A lot of the old aircraft were supercharged. They did have impellers right on the big radial engines on the back of the crankshaft. They did have on even on some of the geared old, the old GO 435s and 480s were GSO. So they were geared, supercharged opposed engines. But as time went on, the airplanes got smaller. It got harder to make a supercharge that would actually work, conveniently. So we went to turbocharging because you got the turbo, you got the exhaust system right there. You can pull the power from that exhaust, extract that heat energy, spin a turbine wheel, which spins a compressor wheel, compress the air coming in and send it on into the engine itself. So it was kind of a free power. It was already there anyway. You already got the exhaust. Think about the efficiency. Typical recip engine is about 33 to 35% efficient, which means you're dumping a lot of heat, a lot of exhaust, a lot of energy right out the exhaust pipe. We turbocharge it, probably comes up all the way to 42%. So we still got a lot of heat going overboard, as you all know if you've seen the exhaust. Original patent on an exhaust gas driven supercharger, aka a turbocharger, was by Dr. Alfred J. Bucci in 1905. Dr. Bucci was the chief engineer for the Sulzer brothers, which of course that's when it was designed. GE got involved. The first turbo diesel engine was manufactured in 1915. And in 1918, Dr. Sanford Moss actually took a turbocharger on a Liberty engine, which was rated at sea level at 350 horsepower. He took it up to Pike's Peak and he boosted that engine to 356 horsepower. And what that did is that proved that the turbocharging theory was correct in that you could maintain or increase a sea level rated engine at an altitude, which is the whole basis of what we're doing today. These are just some pictures. That's what the engine and the setup looked like that he took up the top of Pikes Peak. How he got it up there, I have no idea. I mean, it's just that old monster trying to get there. That's the site where it is. And you see that plaque on the bottom right-hand side of the page. That plaque is actually there, and I have seen that plaque. So I know that it's there. Kind of an interesting thing. It talks about in there of the history of it and how we got to the point we were at. This dude, Major Rudolph Schroeder, in 1920, took a Lapierre biplane. It was 12-cylinder turbocharged Liberty engine. He took it up to 33,000 feet. Now you look at that dude on the right-hand side of the screen. What's he going to do if there's a problem? He's going to jump? Well, that was the idea. That's what he would do. He was in full oxygen for what they had at that day, parachute, the whole bit, and they figured if something happened that he would actually just jump out of the airplane. Well, story goes that he actually got up there, and when he got up there, he basically lost consciousness. And when he lost consciousness, the airplane, of course, was out of control, and his eyeballs froze. Now, his eyeballs froze as he came down into altitude. Apparently, he recovered to make a beautiful landing to complete the flight. Now, if we didn't think there was a lot of whatever we want to call that in the news media today, they were just as rampant as they were back then. And then this other gentleman, Lieutenant John McCready, he actually took the same type of airplane and flew the thing to 40,800 feet. Gentlemen and ladies, this is not a video game. This is when men were men. So why do we turbocharge an engine? Well, power diminishes with an increase in altitude. I think what is like an inch per 1,000 feet. Gain more power and increase engine efficiency. You don't have to physically enlarge the power plant. And we're going to recapture that heat energy normally wasted out the exhaust. Basically, we just want to convert exhaust heat energy into manifold pressure. We can take a little bitty engine and we can make it think that it's a lot bigger than what it actually is by turbocharging. It pushes more air in the engine. You got 5 basic system components. You have a turbocharger, controller, wastegate, pressure relief valve, and intercooler. Turbocharger is just the air pump. Controller is considered the brains. Now remember, this is not a computerized system. We saw that it was patented in 1905. In 1905, there were no computers around that I know of anyway. There are no computers around, so every one of these is a mechanical, hydromechanical device. And they just use different air pressures to determine what the position of things are going to be. So the controller is the brains of the system. The controller controls the wastegate, which is a slave to that controller. The pressure relief valve is nothing more than a safety valve, so you don't blow the engine up. And an intercooler just increases the air density, which we'll talk about in a minute. So if we go to the turbocharger itself, it's nothing but an air pump. It just extracts unused heat energy, normally wasted out the exhaust, which if we look through the way the air is routed and the exhaust is routed through it, you'll see the exhaust coming up through the turbine side, comes around the scroll there, turns the compressor wheel from the turbine wheel, sucks air into it, pressurizes it, and sends it out into the upper deck and manifold pressure. Now watch what happens when this thing enlarges. You're going to see the heat signature from the turbo side coming all the way across through that bearing that's on the left-hand side. That bearing is the one that has the little hole in it there. Now, that bearing, if it is not properly lubricated by you shutting off the engine too quickly, is going to coat that oil that's right in that bearing. And by coating that oil, you're going to squeeze or keep that little piston ring that's in there from actually preventing the oil from going out, because the air pressure won't have anything to push against. And it's going to let you have a leaker on this thing. So it's very important to have proper cool down, which we're going to talk about later. Cold side materials are aluminum. Basically, the compressor side is going to be aluminum. The hot side or the exhaust side is going to be Inconel or stainless steel. We're going to be looking at temperatures approximately 1,615 degrees Fahrenheit. And these turbochargers are going to turn up to about 125,000 RPM. Small ones are going to be the 125, larger ones, let's say 90 RPM, 90,000 RPM. Different models of turbochargers. We have the old Ray J style, which is what we consider our CF600 series. The Ray J company, if any of you have ever been involved with them, turbocharged almost anything that existed between airplanes, cars, tractors, boats. It didn't matter. They'd stick a turbocharger on it. It was easy for them to do because the majority of their systems are what's called a normalized system, in that they are not trying to increase the rated output of the engine. They're just trying to maintain that rated output when they go to altitude. So it wasn't like you had to have a super engine or had to do anything to the engine to put a Ray J on. The Garrett turbochargers, the TA04s, that'd be something like what's on a Cirrus or a Malibu. The Garrett TE06 style would be more like on the like on a Navajo, and a TH08 would be something like a 421, 414 that has a pressurized cabin, because they pull a little sonic venturi on it to pull your air out, which should show you that you have plenty of air. You have enough air coming from a turbocharger, not only to keep the engine at whatever it's supposed to be power-wise, but also to pressurize a cabin. So you got a lot of air coming through this thing. Turbocharger terminology: boosted, horsepower increase. The best way to look at this is on a normalized engine. If you have a standard day, 2992, 1114 millibars, 59 degrees Fahrenheit, whatever, that engine's going to give you X horsepower and X manifold pressure. Never going to be 2992, but just for sake of argument, we'll say 2992. So a normalized system is going to take that 2992 rated horsepower and take it up to altitude of whatever the capability of that turbocharger and the engine are. A boosted engine is going to take the 2992 and it's going to boost it. So instead of having 29 inches of manifold pressure, you could have 31, 45 inches of manifold pressure. Though a lot of the race airplanes and the old warbirds would pull 120 inches of manifold pressure. And think about that's 4 times atmospheric. So I don't think we were too concerned there about durability and reliability. It was probably just trying to get somebody because they were on your butt with a machine gun and you really kind of needed to get out of there. Upper deck pressure. Upper deck pressure is physically from the compressor discharge to the throttle plate. Manifold pressure is from the throttle plate to the cylinder intake port. So you kind of split those up. And the reason we do that is because the controllers use both of these air pressures to determine the position of the pilot valve in the controller to position the wastegate to allow X amount of air to go over the turbocharger itself. Cold section and hot section. Hope you don't need any help with this one. Should be pretty obvious. The cold section is going to be on the air inlet side to the compressor side through the upper deck and manifold to the cylinders. The hot side is the exhaust. If you have a hard time trying to figure out what the hot side is, just run the engine, go out and stick your hand on the turbocharger. You'll figure out real quick which the hot side is. Now we're going to talk about the Garrett a little bit. The Garrett turbochargers, which is considered our 400 series turbochargers, use full floating bearings. They are made from aluminum. They rotate in the bearing housing and on the turbine shaft assembly. So they're constantly turning. They rotate at approximately 1/3 to 1/2 shaft speed. So if you're thinking about it, if we said that a turbocharger could rotate at 90,000 RPM, that means the bearings themselves are rotating between 30 and 45,000 RPM. Probably a pretty good reason to keep some oil going through this thing anytime that turbocharger is online. Piston rings, they use little piston rings. They're not unlike a cylinder ring. They're a little ring that goes on either side of the shaft. They are between the shaft itself and the housing and the bearing housing, and they're not oil retention seals. What they are actually used for is the gas pressure from the exhaust side and the gas pressure from the compressor side push in, trying to get into the center housing, into that bearing housing. Well, we don't want those contaminants in there from that exhaust air and that type. So what we use is we use these rings. The gas pressures push on these rings and they help seal the gas pressures out. And that's what actually keeps the oil in the center housing itself. That's why you might have a situation sometime where a guy says it's leaking or something like that. It's very possible it could leak because there's nothing there. There's no true seal in a turbocharger to prevent the oil from leaking. This is a little picture of the center housing itself. You can see on the bottom left-hand side, those are what the piston rings look like, little bitty things. You also see on the left and right-hand side, you see a couple arrows that moved. Those arrows are indicating that you have a piston ring where the small blue arrows are, and then the air pressure or the gas pressure from the compressor side to the turbine side is pushing against those rings, which is what's sealing the oil inside that chamber inside there where you can see all the yellow inside. If we go to the next slide, it actually shows that the oil inlet pressure is about 30 to 60 PSI. It's got to run the same as what the engine is, and it runs about 3 gallons a minute. Now notice that blue arrow coming down where it says 3 gallons a minute comes down through that yellow section, goes down around, and you can see where the yellow follows around down through the bearings themselves and around the shaft, and then comes down into the bottom portion of that center housing. Notice I've got it marked there's 0 oil pressure. Now this is something that's important because once you have, as we all know, if you have flow, if I take a garden hose and I run water through that garden hose and there's nothing on the end of it, we have no pressure. All we have is flow, just a bunch of flow coming out. If I put a faucet on the end of it, now I can measure pressure because I have a restriction downstream. So that's the same situation with this. We now have a restriction downstream, which is the bearings and the turbine wheel shaft assembly. But once the oil goes through that, there's nothing there. So we have no oil pressure in the bottom of that center housing, which means we have to have a large outlet. Notice the oil drain is 3 times approximately the size of the oil inlet. And in many cases, we're going to have a scavenge pump attached to that to make sure we evacuate all the oil out of that center housing, or you will have a leak. Let's go back to our system components. We had the turbocharger, the controller, the wastegate, PRV, and the intercoolers. Turbocharger's gone. Let's talk about the controller. Different controllers, there's all kinds of different pictures of them. Remember, the controllers to us as a manufacturer, what we see is what the engine manufacturer, the airframe manufacturer want. They tell us, hey, we want an engine that has this much horsepower. It's going to be a 6-cylinder. We're going to turbocharge it. We want this manifold pressure. What do we need to put on there to give us those parameters? And then we just take the basic components and put them together, what would be best for them. You have different types of controls. You have APCs that only control maximum manifold pressure. VAPCs, which control max manifold pressure and part throttle operation. Density and differential controllers, like you'd see on a Navajo. They have the density controls the maximum, differential controls the part throttle. Slope controllers are basically a combination of a density and differential controller all in one. Wastegates. Wastegates are just like they say, hydraulic, fixed, poppet, or mechanical. Most of the ones you're going to see on the airplanes are going to be on in the picture on the top side, top one there. They're a hydraulic wastegate. They've got a little valve assembly in them. You basically have a hydraulic cylinder that moves that flapper on the inside there to route exhaust into the turbocharger or overboard. Now, the position of that valve is controlled by the controller. You have a poppet valve in the controller, and what that poppet valve references, say on a slope controller, is upper deck pressure on one side and manifold pressure on the other. And it schedules oil releasing from the wastegate, which allows either the oil pressure to build up in the wastegate or to be released, and the pressure decreases, which allows the valve itself to open. Fixed wastegates would be something like on the old Senecas with the TSIO 360 engines, where they had a little screw valve inside there, and that little valve, you'd get in there and you'd have to adjust that. Very, very susceptible to overboosting on cold days. You had to really watch your manifold pressure closely and then if you get some dummy like me that went to adjust it for the first time and didn't pay attention to anything, looked to me like it was a loose screw, so I just screwed it all the way in. Well, obviously we know that isn't correct. Obviously there was probably an approved manual out there to tell me how to do that. Poppet type of wastegate, bottom in the picture there, that basically fits right in the exhaust housing. Be like on a big old Continental TSIO 520 WB engine or something like that. Mechanical is just what it says. It uses the first half of the throttle is normally aspirated. The second half of the throttle mechanically closes a wastegate to push the exhaust over the turbine, and that will maintain your engine power as you continue to go up in altitude. So it's a straight mechanical connection, doesn't use oil, doesn't use anything. Pressure relief valve. Just what it says is it's a fail-safe valve, usually set about 2 inches greater than the maximum manifold pressure of the engine. And it basically is there is if the manifold pressure exceeds that limit, it'll open up and just relieve the pressure in the manifold itself, literally, so you don't blow the engine up. It kind of sounds like if it goes off, it kind of sounds like an old Jake brake on a truck, where it kind of goes pop, 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 pop. You'll hear that thing popping as it opens and closes to maintain that pressure. It should never be the controlling factor. If you have a pressure relief valve, a PRV that's actually controlling, either there's something wrong with the PRV and it's weak, or there's something wrong with your control system on the turbocharger itself. And finally, intercoolers. I don't know what, 10, 15 years ago, remember they came up with, a couple companies came up with intercooler kits, and they put them on, I think a lot of the 210 series aircraft and the big Bonanzas and things like that. And what they did was, they can't say that they're going to give you more power, but what they did say was they could increase your altitude. Because remember, when have a turbocharger, the higher we get in altitude, the harder it's having to work to compress the air. The harder it has to work to compress the air, the hotter it gets. And if you get it too hot and push it in the cylinder, you are looking at detonation. So that's what limits your altitude on most turbocharged engines. There's nothing to do with what the turbocharger could actually provide. It has to do with how much heat is being generated so as not to cause damage to the engine. So we come up with an intercooler. The intercooler itself cools that air charge going into the cylinder, drops the temperature after it comes from the compressor, before it goes into the cylinder itself, and you can run a higher altitude because you don't reach your temperature limits. Remember, it can't change the certification of the engine. What it can do is help it get there. Okay, so here's the picture of Cirrus engine. It's TSIO 550K engine, and you can see that the components are wherever they need to be. I mean, logically, obviously, the turbocharger is going to be in the exhaust system, and the wastegate is going to be really close to the turbocharger. In this particular case, it uses a dual turbocharger setup, and the dual setup means nothing other than they didn't want to expend the room for one large turbo. They can make a nice, neat, smaller package by just splitting the turbo into two. Means no difference. Turbo doesn't care whether there's two of them running or whether there's one running. Still going to do the same thing. Wastegate still is going to bypass the turbocharger to maintain whatever manifold pressure it's supposed to be set at per what the controller tells it to do on the top of the picture there. And of course, then you have the pressure relief valve in the manifold, and you have an intercooler on either side to cool that air charge going to the cylinder itself. Turbocharger is sensitive to insufficient lubrication, contaminated lubricants, foreign object damage, and of course, extreme temperatures. Let's take a look at some of those. So here's insufficient lubrication. You got enough friction. You can't really tell on this shaft from the picture you're seeing, but this shaft is actually blue. You can kind of see it on that left-hand side of the shaft itself. But if you look on the right-hand side, you see some like white that looks like aluminum. That is aluminum that's galling, where the aluminum material has transferred from the aluminum bearing onto the steel shaft itself. And it did that because there was enough friction, created enough heat, and it stressed that portion of the shaft. When you have insufficient lubrication on a bearing like that, especially when it's a plain aluminum bearing, what's going to happen is you're going to tear out some of that inside of the bearing. When you do that, instead of the bearing spinning freely, like going, like that, you're going to get an orbital motion. It's going to go whoop, 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 whoop. And as it turns like that, now the shaft's going to start to flex. When the shaft starts to flex, now it's going to move the wheels. And as the wheels start to move, they're finally going to contact the housing, and you're going to destroy the turbocharger itself. Damage to bearings, turbochargers, we recommend oil changes and such at 25 to 35 hours, and that's what the manufacturers go by. We don't bother, we don't care what kind of oil you use, if it's Phillips or Aeroshell, whatever you like to use. Whatever's approved by the manufacturers, what we have to approve for the turbocharger, because logically there wouldn't be any other way we could do it. Foreign object damage, bolts, valves, rocks, rivets, alternate air doors will break pieces from the blades or machine them down. I have seen everything you see on this screen. I have seen inside a turbocharger. So we'll get these things come back and they are actually damaged. The next thing is determine how did that happen. So let's look at a couple. So here's some FOD damage. This came down from a cylinder. That's an exhaust valve remnant. You can actually see the valve portion itself came down, whacked the turbine wheel, knocked the ends off the turbine wheel, and of course the efficiency and balance went to crap right there. Actually, I would imagine the balance wasn't all that bad, because it looks to me, if I look at this picture, that it's pretty much knocked the same amount off of each one of those blades, but kept it probably reasonably balanced. They probably didn't know this, except they lost. They couldn't get their critical altitude. They couldn't get their power. Something is what they were looking for. And of course, then they found pieces of the exhaust valve in there. This is the intake on the compressor side. So you have your compressor wheel, and notice that these blades are damaged on the leading edge of the blades. So that leading edge damage is because something came in from the inlet, whether it be through the inlet itself, whether it be the air filter screen, whether it be the alternate air door, whether something got left inside the intake, hard to say, but something hit the leading edge of this turbocharger compressor, and by doing that, it's damaged that wheel. Now, the next important thing is, if you have something like that, where's all that FOD go? I mean, think about it. That FOD's going up into the upper deck, and maybe if you're lucky, it comes out of the compressor, goes into the intercooler, and gets captured there. Otherwise, and maybe even so, it goes on into the engine cylinders. Now you got these pieces of aluminum coming off that wheel bouncing around inside the cylinder. So we have to recommend that anytime you have damage like this on a compressor wheel, you are also going to bore scope the engine, make sure you don't have any internal damage on the engine itself. Just a side note, the nut that's right in the center of that turbine wheel assembly on that compressor side, we are now slowly changing those nuts over so they are reverse rotation. Because if you think about it, if that thing is turning at 90,000 RPM, that wheel, and something tries to stop that wheel, the wheel is going to stop, but the shaft is going to keep moving. And when it would do that, it would loosen that nut. The nut would come off, and now it goes down into the system itself. Okay, so by using reverse threads like an old Chrysler wheel lug, by using reverse threads, it can't do that anymore. Here's some soft FOD. Notice the wheel. Notice the wheel itself is actually bent backwards. And that's what will happen if you have soft FOD go through an engine, go through the turbocharger. It will cause the blades to bend backwards because they're spinning along 90,000 RPM, say. Something is introduced like a shop towel into there, and it grabs on that shop towel, and the blades, the shop towel pulls the blades backwards. Now, you've seen this damage on these compressor wheels. First one and now this one, there are no repairs on any of this. Once you've bent one or once you've got nicks or something in a blade, you are replacing that wheel. You cannot repair. There's no blending or anything like that that you're allowed to do. Here's some FOD that was left in here. Notice that yellow cap plug. It's right in the middle of the screen there. That cap plug basically was put in the inlet, oil inlet of the turbocharger center housing to prevent contamination. The theory is you're supposed to take that cap plug out when you put the fitting on. In this case, that did not happen. The cap plug ended up inside the center housing, blocking the oil outlet. And when it blocked the oil outlet, it allowed that turbocharger center housing to fill up with oil, which of course then just pushed it overboard because there was nothing there, as we know. There's the piston rings are not going to stop it, and overboard it goes. That's when the tower calls you up and they tell you, hey, you got a white mist coming off the right side of the aircraft. What are your intentions? Next one, if you can see this picture, excuse me, if you can see this picture clearly, and if you notice kind of in the middle of the picture, there's a round section of that gasket. Now, in your mind, take that section and make a circle out of it. And when I see something like that, what I see is an inlet oil gasket was used on the outlet oil side. Again, you restricted the oil flow coming from that center housing, allowed the oil to back up in that center housing, and you were pushing it right out the turbine wheel assembly and into the turbine and compressor housing. Some general condition stuff. All right, that's one of my favorite pictures. I like this picture. And the main reason I like this picture is because I know it's not airplane. I mean, you're sitting out there saying, it's not an airplane engine. Well, it's not an airplane engine. So I'll tell you that right off the bat. You don't have to guess at that. But it does show a turbocharger in action. And this is one of the important inspection criteria that you need to be careful of. Because what happens is, if you look at that thing, I mean, it is glowing. It is so hot, it's white, and it's almost translucent. You can almost feel that you could see those blades turning in that turbine side that you can actually see. Seems like you can see right through that housing. That's how hot these things get. So you got to be careful, because when you're doing your inspections, you got the thing sitting on in the shop there, and you got everything uncowled, and you're having your morning coffee, you got your arm, propped up on the turbocharger. That is not how it operates. So when you're doing your inspection, you need to make sure that all the torques are completed properly. You don't have small cracks in a turbocharger. You have no cracks in a turbocharger. And you got to look at it the way it operates, not the way that you're seeing it when you're doing the actual inspection. And that's sometimes hard for people to get through their head, is this is when it's really operating. And that's what you want to have in your mind when you're inspecting it. And this picture actually is a picture of the exhaust. It's on, I think it was on a 414 or 421, can't remember. A gentleman was at one of the seminars we did, and he said, every time I fly at night, I see this red glow in my cowling, and I'm always concerned. And I said, really, the only time you need to be concerned is when you don't see that red glow, because this is telling me that the turbocharger system is just humming along, and this is exactly what he should be seeing. But it is a little eerie if you've never flown at night, and you see this, it's like, yeah, that's pretty good. We had an old Hiller helicopter, had a big turbocharger sitting on the right-hand side. It was like a TVIO 540, some big old engine with a giant turbocharged vertical engine for helicopter, and sat on that right-hand side. We used to give rides with this thing. Worked fine during the day. Nobody would get in it at night. because that thing would come down, and helicopters are pulling pretty much all their power when they're coming down to land, and that thing is out there just glowing red, and we could not get anybody to get in that helicopter. So that was a daytime flight only for giving rides on that ship. General condition, shaft spinning freely. The old Ray J styles, they do actually have a seal. So I kind of been lying to you the whole time. On the Ray J style, as compared to the Garrett style, there is a labyrinth, a carbon-faced labyrinth seal that's in that compressor side. And what that does is got a spring on it, and it actually is a true seal because they're trying to keep the oil from going up into the compressor housing. Garrett has just decided that it wasn't there. There was just no value in that. If you get a little oil in the intake side, who cares? It just pulls it up into the engine, consumes it, and it's gone. So it's really no big deal. But Ray J actually thought it was important, so they did this. Curiosity is we tried using this seal, the same type of seal from the Ray J style, and put them in the Garrett turbochargers, and it didn't work at all. It was absolutely worthless. So we just went back to what the standard was, that, why mess with something that's worked since 1905, which has probably been upgraded a bit since then. Light source, general condition, you want to see the back of those blades. So you're going to look inside there and you're looking at the back. Don't worry about on the turbine side. Don't worry about the front of the blades there. Look at the back of the blades. That's where your damage is going to be. And I know it looks like it's hard to get to and hard to see, but if you look carefully, you can actually see the curvature of that blade going up in the back of the turbine. It's on the turbine wheel itself. If you ever see one that's broken, you will never have a problem finding one again, because once you've seen it, you really know what you're looking for then. Of course, you could always use a borescope. You could take a borescope and run up there too, and you'd see the same thing, maybe even better. Can't have wheels contact in the housing. Turbochargers have blades, obviously, just like this shows, and they are susceptible to the same thing turbine engines are when they talk about creep. A creeping blade is due to over temperature and over speed. And what it does is centrifugal force pushes that blade out or pulls that blade out, and that will allow it to contact the housing. You can see the rub marks on the wheel itself, and you can see the contact marks on the compressor housing. Radio checks and axial checks, end plate checks. So let's go back to the other one. Radio checks are up and down. Basically, you're putting a hand on either side of that turbine wheel assembly, put a hand on the turbine wheel, put a hand on the compressor wheel, and lift up and down. You should have a small amount of movement. There's a bunch of numbers there that tells you what they are for specific turbos, but basically you're going to get in there, and if you can feel a little bit of movement up and down and doesn't go clank, 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 you are good. Same thing on the end play or the axial play. You're now going to move it in and out. Now, you can get all these different fancy equipment and stuff like that, but it's been my experience that you are either going to have the correct amount of play, you are going to have a whole bunch of play, which means that you're done anyway, or you're going to have no play. The no play is the most interesting one, because if there's no play, that tells me that the turbocharger housing and shaft assembly has built up a lot of varnish and soot and stuff inside that housing, and by doing so it's now blocked and won't let anything move freely. However, odds are when everything warms up and everything expands to its normal operating temperature, there won't be a problem with it. But that's the type of thing where you want to tell the guy, tell your customer, hey, you may want to pull this thing down. Let's pull the turbocharger off, we'll send it in, have it cleaned up, and get you back to where you're supposed to be on the clearances. He's going to say no because he's cheap, doesn't want to spend the money. Well, down the road, when the turbocharger does fail and doesn't work properly, you will have that moment in time when you can say, I told you so. Over temp, notice the over temp there. Now there's your piston ring. I don't know, you can see it in that picture, but it's hard to see. But what's happened here is the temperature has gotten so hot that it's actually taken the contaminants that are in the oil, normal contaminants, and it's taken that heat and it's literally welded that piston ring right into that shaft itself. You can kind of see where it goes around there, and you can see the deposits there around it. It's just like a welding rod deposits there around that. Now here's one that had 60 hours on it in 15 months. And this is what it came apart looking like. 60 hours. That's all this thing had on it. And there's your piston ring in there. Look at all the contaminants that are in there. That's a lot of rust. It's a lot of coke, a lot of carbon, a lot of just garbage that's inside that center housing area. This happened that quickly And Continental has a bulletin, it's M71-21, written in 1971, that does say you need to run these things, especially when they're brand new, to get that coating of varnish and stuff on the shaft, because if you don't, every time you start it, you're grinding that rust off and dumping it inside the turbocharger. That's the bulletin. It's still an active bulletin that was made in 1971. And this is the one that actually was the beginning of it from Air Research. This was written in 1969. Both of these documents are still current, and they could still be used for maintenance because they are the most current data. The interesting about this one is if I look at that bulletin and I count, looks to me like I got 1, 2, 3, 4, 5. Looks like I've got 5 paragraphs, and they wrote an entire bulletin in 1969 in 5 paragraphs. 5 paragraphs now wouldn't even get us through the legalese that has to be in a service bulletin, as you all know when you try to read them. Contamination. Think this is contaminated? I don't know. Looks like it is to me, considering it won't turn anymore. It probably is. But what is the contamination from? Is it operational? Is it environmental? I'm going to say it's a little bit of both, because remember, you got a lot of crap coming down from that exhaust that gets into that turbine assembly, and all that mixed with some nice, warm, moist air sitting in South Florida is going to turn that stuff into that crap that's inside there. And eventually it's going to build up enough, it's going to stop the turbocharger from turning. And if you want to see something even better, here's your wastegate that came out of that same application. And you can see that how it would ever seal to do anything, I wouldn't know. It's pretty, it's got a lot of contamination down inside there. So this gentleman pulled them off. These came in as cores. It's interesting when we get cores in our core facility out there, you know, they tear a lot of stuff apart and all. And once in a while, they will call me up and they'll say, you have got to come out and see this thing. Well, let me tell you something. If they tell me that, I drop immediately and I go out and see it, because these guys do these tear downs every single day. And when they see something that they think is interesting, I'm going to go see it. I want to go see what they're actually talking about. Here's a whoops. Now we're going to do some whoops now. Excuse me. So this gentleman was on an Aerostar. It was a twin turbo Aerostar. So of course it's multi-engine, 2 turbochargers on each side, and one of the engines could not make manifold pressure. So we went through all the different things we could think of and all the things you would try and all. He got pretty upset. So he went ahead and overhauled the engine because he figured it's got to be the engine that's causing the problem. Put the turbos back on again because they were only, I guess, part-time turbos, 600 hours, something like that. Put the turbos back on, brand new engine, did exactly the same thing. So you can imagine he's about to pull his hair out. Won't operate like the left engine, and basically it would pull power, but it wouldn't get to its critical altitude. So where the left engine, say, I can't remember which engine, but say the left engine, as he was climbing out, could go on up easily and do his, 18,000 feet. The right-hand engine started stumbling at 15,000. It just couldn't maintain it. So we finally got fed up and just said, hey, dude, how about you just send that in to us and we will test that turbocharger for you. But I said, before you do, take all the fittings off, take any brackets off. We don't want any of that stuff coming in, because technically, if you send us any component, alternator starter, no matter what it is, and you send in an airframe component that's attached to it, we technically cannot send that back to you because we can't, we're not authorized, it's not our product. So we can't give you an 8130, we can't inspect it, we can't do anything. So technically it has to go in the scrap bin. Now, of course, we try to avoid that. So in this case, I told this guy, before you send in, send me a picture. I want to see what this thing looks like. This is the picture that he sent. All I have to do is look at it. And if you look down the center, right down through the center, and you look at the turbine wheel, and you look at about the, let's say, 3 to 4 o'clock position, look at the gap between that turbine wheel and the housing itself. In 2 seconds, you should be able to make a determination that if that wheel is that far away from that housing, you are not going to be able to extract the correct amount of energy from that exhaust. And the more you push it, the more you're going to lose, which means it was stumbling and falling on its face at approximately 15,000 feet, trying to get to 18.5 or whatever it was. As it turns out, this particular turbocharger has an incorrect housing on it. That gentleman was not a happy camper. Here's another error. This was a turbocharger that came back to us. It came back for warranty because it would not torque. It properly would not torque. And if you notice, when you get a turbocharger that we would send you in a box, it's basically clocked. I'll say clocked. The compressor housing and the turbine housing are clocked for shipping. So they're both probably pointed the same direction. So they go in the box nicely and pack up and all that kind of stuff. Well, you're going to have to go ahead and clock these properly for the installation. So on a series, you're going to take this thing and you're going to bolt the flange on the exhaust, just bolt it on because that's your hard point. And then you're going to rotate the housing, the compressor housing and the center housings. You're going to rotate these to line your oil lines up and to get your compressor lined up with the outlet, with the outlet of the turbocharger or the compressor side itself. So when you're doing that, you're going to rotate this thing. Well, this gentleman, what he did is he took the center housing apart. And what he did when he did that is he turned it approximately, I don't know, what do you want to call that? He went from like 10 o'clock to say 11:30. And apparently put it together there, screwed everything together, but apparently wasn't lined up properly. So then he moved it from approximately, say, that 11:30 position to let's say a 1 o'clock position and screwed it down again. He decided apparently that must have been the place it needed to be, but the problem is he couldn't get torque. Well, he couldn't get torque because he's not putting the fastener into a true hole. He's created this. And of course, he sent it back for warranty because everything comes back for warranty that way. And he said that he couldn't get torque. So what we did is we looked at the thing and said, something's wrong. I mean, the way you did this was wrong. Well, in the end, he told me that, of course, it wasn't him that did it. It was one of his guys working for him and he wasn't paying attention to him. And that's how that happened. And I met this gentleman and I thought he was going to probably walk up after the presentation and knock me on my butt. But he was actually he was a very gentleman about it. He told me, he said, hey, that was me that did that. It was a stupid mistake. And I said, well, since I know who you are now, I'll pull it out of the presentation. He said, don't you dare. He says, you leave that in there so that everybody can see how you can do dumb things sometimes. All right, turbo oil leaks. Drain ports must be down. Most of the time, it's not going to get too much for you. Once you've got it lined up with your oil lines that are already on the airplane, you're probably in pretty good shape. Drain leak, no slope. Any slope in the line is going to give you any sink traps. Hoses for delamination. I have made a turbocharger hose, delaminated the inside because I cut that inner liner, put it on the turbocharger, had a lack of oil flow, burned up the turbocharger, bought a second turbocharger, put it on, burned up the second turbocharger. But even I'm not that stupid and decided that there must be something else wrong. And we finally found out that I cut the inside of that hose and created the lack of oil flow to it. I don't make hoses anymore, by the way. Sludge. This is one thing you can check. Look in that center housing. Take the outlet of the center housing off, the oil outlet, stick your little finger up in there and see how much crap and sludge is built up inside that housing. That is restricting oil flow. Now, we do not technically have a way to fix that, but if you go to some of the websites out there, like maybe for Ram aircraft, they will be able to tell you they have a process for doing that. We don't have an approved process. But you're not going to hurt anything by doing it. Just always remember that you have to pre-lube the turbocharger if you break the oil lines. And of course, faulty check valves. That's probably the biggest thing going on right now is faulty check valves. So watch your Lycoming and your Continental installations. Overspeed, overshoot, and overboost. They're exactly what they say they are. So really not too much there. Overboost obviously is when you exceed the limits of what the engine was tested and certified for. Pre-inspection. I mean, this is you guys, you know what you're doing out there. You're doing your inspections, follow your checklist, tells you to check these different things on the turbocharger. Watch your clamps. These V clamps are probably the biggest things the feds are looking at right now. They're not being torqued properly. 9 times out of 10, they are over torqued and these clamps are cracking. And when they crack, of course, the clamp comes apart, housings separate, and you've got fire and hot exhaust gases in the engine compartment. Cool down. This is one that always starts it with everybody. What's the cool down recommendation? To me, it comes down to what the POH says. If you look at the POH for the airplane, it should tell you how to do this. Basically, the Cirrus does not. But if you go to the Continental engine manual, it does tell you how to do this. 600 series, the Ray J's need no cool down because they're aluminum housings. So they are able to dissipate the heat. If you have a normalized system, it's going to be off the air. The turbocharger hasn't been turning since 3,000 feet. So you're probably in good shape. But you mechanics, you better watch it because you are out there running these things up to full static power. You find something wrong, you pull the engine down, you shut it off, and that turbocharger's out there humming. So you can cause as much damage as any dumb pilot out there. We do have different videos. We have different video online testing. And it's kind of interesting because you all can take these things and use them with your shop. These things probably run, I'm going to say 2 to 4 minutes for each one of these. And they are a great starting point for you guys to take to your shop, to your folks there, and run them through and then discuss them and say, hey, here's what we did on the PDT. How do we do it? Per mold gear coupling installation is the biggest thing the feds are looking at right now. Turbo bearing clearance, how do you check them? Electrical troubleshooting, turbocharger cool down, starter duty cycle, all these kind of things. You can watch these things with your teams, discuss them. How are you doing it compared to what probably is approved, and then move on from there. And you can spend a half an hour and you can get some good training for all of your folks at the same time. So it's a great troubleshooting exercise. It's a great, what do you call it? Synergy, where you get everybody all together and you're all on the same page and how you're going to handle some of these things. And with that, I want to thank you. It's been a pleasure, and I hope you all gained something of value from the presentation. Our contact information is product and technical support, Hartzell Engine Tech, 2900 Selma Highway in Montgomery, Alabama. There's our tech support email address, and we have 2 phone numbers. One, if you can use 887 numbers, 800 numbers, and the other if you can't. Send us an email. We'll be glad to help in any way we can.